Kirchoffs laws. This is one of the important laws in the electronics. So before this, we have heard about what is called as the Ohm's law, very famous. That is nothing but V is equal to IR or E is equal to IR. Actually, it is V proportional to I. Voltage is directly proportional to I at a constant temperature. If the temperature do not change, then the voltage is directly proportional to the current. So this Ohm's law is applicable, is used if the network is very small. If the network is very simple, then you can find how the current is distributed and how the voltage are distributed in the network. But if the what do you call, if the circuit is very complex, the circuit is very complex, then one cannot use the Ohm's law. One cannot. We can use, but the work or the calculation becomes very tedious. So hence we go for Kirchoffs laws. After Kirchoffs laws, many theorems are there. So basically Kirchoffs laws, there are two types of laws. One is KCL, other is KCL, KVL. KCL is nothing but Kirchoff's current law. KCL is nothing but Kirchoff's current law. So what does this law states? Before going to what does this law states, this law is based on law of conservation of charge. It is based on what law? Law of conservation of charge. And what does it say? Sigma I is equal to 0. That means what? The algebraic sum of currents. The algebraic sum of currents at a point is 0. You have to specify at a point or at a node or at a junction. These are the three terminologies: point, node, or junction. This you have to specify. The algebraic sum of currents at a point or at a node or at a junction is equal to 0. That is one definition. And the second definition is that sum of currents entering a node is equal to sum of currents leaving that node. This is another definition. Sum of currents entering a node is equal to sum of currents leaving that node. So that means it is just like a node or a junction or a point. Example followed. So sum of currents entering a node is equal to sum of currents leaving that node or a junction. So if I say junction in real time, example, if I take a railway junction, you know very good, a railway junction. If I take a railway junction, what is the railway junction? What happens at the railway junction? The railway junction, what happens? Many trains comes, halt, and they leave. Right? If I take a Vijayawada junction, so many trains come, halt there for some time, then leave. That means number of trains that are coming to that junction is equal to number of trains leaving that junction. So same thing, sum of currents entering the point is equal to sum of currents leaving that point or a node or a junction. For example, if I take an example, consider this is a node N, consider that is a node N. So let us say I1 is one current, I2 is another current, I3 is another current, I4 is another current, I5 is another. So here there are some sign conventions you have to take. This is very important. Sign conventions are very important in the Kirchhoff's current law or Kirchhoff's voltage law. In Kirchhoff's current law, any current entering a node is considered as positive. That means current entering is taken as positive. Current entering a node is taken as positive. Similarly, if the current is leaving from the node, current leaving that node is taken as negative. Current entering the node is taken as positive, current leaving the node is taken as negative. That sign conventions compulsory you should be able to know. Then, if I take this example, let us start from I1. I1 is the current, you can see the direction. I1 is the current that is entering a node. Entering means what? Positive. Positive. Then, I have to sum up and equal to 0, right? Sigma I is equal to 0. Next, I2 is the current which is also entering a node. Plus I3 is the current which is leaving the node. So what happens? Minus I3. Minus I3. Plus I4 is the current also leaving the node. Minus I4. Plus I5 is the current entering the node. I5. So I1 plus I2, this must be equal to 0 according to Ohm's law, that is Kirchhoff's law. Plus into minus minus I3 minus I4 plus I5 equal to 0. I1 plus I2 plus I5 equal to I3 when goes here. So what are I1 and I2? The currents that are entering a node. What are I3 and I4? Leaving the node. So sum of currents entering the node is equal to sum of currents leaving that. So that is called as the Kirchhoff's current law. Kirchhoff's voltage law. Kirchhoff's voltage law is based on the well-known Ohm's law. Kirchhoff's voltage law is based on the well-known Ohm's law. So, according to that, what does Ohm's law states? V is equal to IR. V is equal to IR. Or in someone will write it as E is equal to IR. Anything. Either V is equal to IR or E is equal to IR. So it is a Ohm's law. If I put a summation, I will write it as this one is equal to summation I into R. Summation, that is sigma E is equal to sigma IR, then that is called as the Kirchhoff voltage. That is what I am saying. The voltage KVL is based on the Ohm's law. Just put sigma on both sides, summation. Then it will become a Kirchhoff's voltage law. So the algebraic sum of potential drops or EMFs. So E means voltage, we can call it as EMF or potential drops. The algebraic sum of potential drops or EMF is equal to the algebraic sum of the product of their currents and. So again there is sign conventions here. So be careful in the sign conventions of KVL, because in KCL only two are there conventions. Here you have to take four conventions. The first convention is that if I have a battery, this is a battery, this is the positive terminal, this is the negative terminal. So in my analysis, when I am moving in this direction, such that I am moving from negative terminal to positive terminal, lower potential to higher potential, because plus is always higher. So if I am moving from negative to positive or lower potential to higher potential, the value of voltage is taken as positive. So moving from negative to positive terminal, voltage is taken as positive. So whichever terminal you are leaving, you are entering in negative terminal and leaving the positive terminal. So you have to take the value of positive terminal. If the analysis is reverse, if I am moving in this direction, I am moving from positive to negative. So we have higher to lower potential. Which terminal I am leaving? Negative terminal. Entering is positive, leaving is negative. So what is the value of voltage? Negative. So moving from positive to negative terminal, voltage is taken as negative. So this is the sign conventions about the voltages. And now the current comes into the picture. For example, the current is flowing in this direction and I am moving in this direction. The current is flowing in this direction from right to left and I am moving from left to right. That means I am opposing the direction of current. I am opposing the direction of current. If I am opposing the direction of current, opposing direction, current is negative. Current is negative. If I am opposing the direction, the current is what? Negative. If I am moving along the direction of current, if the direction of current is this one, and I am also moving the same direction, if I am moving along the direction of current, then I will get positive. Along direction, along same direction. Current is considered as positive. Current is considered as positive. So you have to remember these four sign conventions. Two for voltages, two for current. For if you take the current, if you are moving along the direction of current, take it as positive. If you are moving against the direction of current, take it as negative. For voltages, if you are leaving the positive terminal, take the value as positive. If you are leaving the negative terminal, then take it as negative. So let us see an example. So let us take this example. And mind you that the KVL is applied only to a Loop. Loop means it should be a closed circuit. It should be a closed circuit, not an open circuit. So this is a closed circuit. If both are not connected, then it becomes open circuit. You cannot apply a KVL. For KVL, it should be a closed circuit. Then this is the given E1, E2 are the two batteries, R1, R2 are two resistances, I1 and I2 are the currents. So I1 is flowing in clockwise direction, like this it will flow, right? I2 is flowing in anti-clockwise direction. Now, we have to choose, that is our current direction. We have to choose our analysis direction. So in which way you want to move? Either you want to move in that is clockwise direction, or you want to move in the anti-clockwise direction. That you have to decide. That is our wish. Anything. Either you do clockwise or anti-clockwise. So here I want to move in clockwise direction. I want to move in clockwise direction. So let us start our analysis from some point. I am starting from point A. Now I am moving because I want to move in clockwise direction. I am moving like this. So I am moving from negative to positive terminal. Which terminal I am leaving? Positive terminal. If I am moving from negative to positive terminal, voltage is taken as positive. What is the voltage? E1. It should be taken as positive. That is equal to. I am moving like this. Because I am moving in anti-clockwise. I1 is the current which is also moving in same direction. I1 is also moving along with me. I am also moving along with I1, right? So a current is moving like this. I am also moving like this. So same direction is there. So the current I1 is taken as positive. It is flowing through what? R1. So why I have to write like this? Because sigma E is equal to what? Sigma IR, product of current into resistances. Then I am coming like this because this is finished. I am coming like this. Now I am moving in the backward direction. I am moving in the backward direction. But I2 is the current which is moving in the forward direction. That means I2 is moving like this. I am moving like this. So both are opposing the direction. Since both are opposing the direction, value of current I2 must be taken as negative. It is flowing through R. Then come here. Moving from positive to negative terminal. Positive to negative terminal, voltage is taken as negative. So minus E. And again return back to the same point. So in this way, you will write the voltage equations by using the K